Ooh, Kaltura decided to work. Okay. So, just as our final recap, and for people at home, right, you're going to build me this. So you're going to test this module in a test bench, and you'll take pictures of your time areas. You'll then build this wrapper. You do not test bench this. You'll just hook clock to clock, button C to reset. The most significant bits will come out into digit select. Pick any old number you want, put it into data. All right. 0 to sign, 0 to hex to desk, because we don't care about that. We don't care what the number is. This will output to their appropriate things, seg, DP, and anode. And you're just going to look at that, and you should get 4 nicely appearing numbers that look like it's simultaneous and not dim. If it is too dim, you need to increase N. If it's blinking, you need to decrease N. So in your lab report, you will show me a picture that all 4 are correct, and you will give me your value of N. All right, so that's what the first part you're going to have to do. Second part. Sorry, I started drawing this, and now I ran out of room on the edge. Okay, this is what you built right here. You'll notice this. This is your 7 seg 4. With this is your N count, and the 2 bits coming in. Clock is hooked to clock, and button C is hooked to reset. So this is exactly what you have so far. This is your calculator module from last lab. All right. If you remember, we had button U set to load the calculation, right? You've done the calculation at this point, and this tells you to load that value into the output register. So I just called that load calc here. We had a button D, which loaded into data 1. That was the upper register to the ALU. We had switches 7 to 0 hooked to data. We had switches 11 to 8 hooked to the opcode, clock, and button C to reset. So this is exactly what you had on the previous one, even including the things hooked up that way. This was your output. Your output was 16 bits. 15 to 8 was the answer, and 7 to 0 was data 1, this register before the calculator. And you hook those to an LEDs. Okay? We're now going to take 15 to 8, the answer. Okay? So you'll take whatever this output wire is called, bits 15 to 8, and we're going to make it into a new thing that's going to calculate a conversion from 2's complement into a magnitude and a sign. Does that make sense as a goal? Now, this might sound complicated, but it's amazingly simple as a module. Right? And then that data output, this will just be a positive number. We'll hook that into data at 16 bits, and our sign will hook to sign. We'll leave the hexadecimal on switch 15, just like it was in the lab 8. And so this will be exactly what we've had before. This will be what was just hooked to switch 15. So this will just convert our answer. So you should be able to enter in a piece of data, load it in to the data register, pick a second number, pick an operation code, load the result, and that result should display now in your 7 segment. And it should be in a readable format with a sign and a magnitude. Does that make sense as a final goal? So the only thing we have to do is this. All right, we've got 8 bits coming in. We need 16 bits coming out. All right. So we're going to draw kind of a big picture. Data in. And it's 8 bits. If I have an 8-bit number, how do I, and I assume it's in 2's complement, how do I know if it's positive or negative?
First value is 1.
Yeah, I look only at the first bit. Does that make sense? So I can grab from here the most significant bit and I can run that immediately out to the sign bit. That's all I need to do, right? I can run it right out to the sign bit, whatever is the most significant bit, because you told me that tells me the sign. If it's a 0, it's not a negative number. If it's a 1, it is a negative number. So that done. Right? That is the easiest thing you ever do, right? Assign whatever the sign output is equal to the most significant bit of your data. All right. Now, we have two possibilities for the magnitude. Right? It could be a positive number. Right? The most significant bit was 0. What should I do in that case? What is the magnitude? Let's pass that number straight out. Right? What if it's a 1? If the sign is a 1, then what do I have to do? I have to take the 2's complement. So I have two possibilities. I have to pick between them. How do I pick between two possibilities? Yeah, an if statement which builds a mux. All right, so I will have to my value coming out, which needs to be 16 bits. I'm going to have a mux. If it's a 0, right, then I'm just going to want to take whatever my number is, append some zeros, and pass it out. And the thing that decides is the most significant bit. So if this is the case, I'm going to take my full data in at 8 bits, and I'm going to append 8 bits of 0. 0, 8 more bits. I'm going to append them together, and I'm going to pass those through. You agree? Okay. What if, how do I do a 2's complement? Because that's the only thing that's left. I got to figure out how to do a 2's complement down here.
Invert all the values and add 1.
Flip all the values and add 1 is a perfectly fine way to do it, right? How do I flip all the values? Let's just do a bunch of NOT gates. In this case, it's not a conditional guess. We just know what it is. So I can take these 16 bits here. I can grab them, and I can negate all of them. Literally, just not each bit. Remember, NOT allows a bitwise version that'll just not every single bit. So that's really easy to do. All right, so as long as you use tilde and not bang, you're in good shape. So that's going to be fairly straightforward. Then how do I add 1?
Put it in an adder with 1.
And I'm done. This is an if statement. All right? This is just curly brackets appending a 0. This is taking that and negating, which is a tilde, and then adding 1. You could do that on one line if you really wanted to. Append the 0, not it, add 1 to it. Yeah.
If you're negating all the zeros, you get a bunch of leading ones.
I do. And when you add 1, because remember, it was leading ones that's on, right? Well, actually, so we should be real careful. I should actually, so technically speaking, I should sign extend the most significant bit. So actually, let's take these. Actually, that is a very good statement on your part, and I was being careless. Append 8 bits of leading 1. Let me do, it's got all messy here. Let me put this outside. I'm going to have this, and I'm going to have appended to it, to my data in, which is 8 bits. I'm going to have to append to it on the most significant bit side. I'm going to have to put 8 bits of 1. And the easiest way to do that is 8, 1. that means 8 ones repeated. And this is another one of those. So if you remember, curly brackets extends things. Comma lets you append things. If you want to do something multiple times, you put the number of times you want it done before the curly bracket, and that repeats them. But you have to embed it in another curly brackets to work. So we'll take this, we'll stick them together, we'll negate it, and then we will add 1 to it. And this replaces that up there. That makes sense? So all that, this really just changes this a little bit here. That I just put for reference. Okay, Verilog code, what would that look like? This is a module, right? So inside this, I might have to have an always. I might have to have an if. That's this selector. I'm going to put this in kind of pseudo language. You're going to have to convert it, right? So if, and we will use the most significant bit. Now, the most significant bit is technically one binary bit, so I don't have to compare it to 0 or 1. I could just put it, right? Because it is a selector for it. So if the most significant bit is a 1, you'll have to do this, right? So you'll do this calculation right there. Else, you'll do this. Does that make sense? That builds both of these. And this is a very simple thing. Assign the output to be equal to the most significant bit. So this is a very, very short module. You will then test it. Right? This is something that you can actually test, give it a few different numbers, some positives, some negatives, and see if it outputs the correct numbers. Right? If it does, then you'll just stick it into here, and you will build it. And then try it for a few numbers, take pictures showing the correct answers, work it out. Do some calculation that makes it positive, do some calculation that makes it negative, and it should look good. Does this make sense to everybody? Yes. So what I'm going to want to see will be 4 things. I'm going to want to see the test bench for this and its output. The test bench for the counter and its output. I'm going to want to see the build for the whole wrapper thing that you're doing right now with the value of n, right? So a picture of this showing that it worked and the value of n. I'm going to want to see the test bench for this, which is our 2's complement converter. All right, so I want to see a test bench for that, and then you will build this whole thing, and I will want to see a picture of a positive and a negative number for your build. All right, so you'll do like an addition and show me the value, do a subtraction and show me a negative value. Does that make sense? Yeah. Those things, that is the deliverables I want. I do not want the deliverables in the lab, because otherwise that's going to, they make you do all kinds of crazy stuff. This is actually much, much simpler. Right? And remember, simple, clean designs will kick, right, a confusing design. And the big thing that was confusing in this is they have multiple counters and ticks passed between them and stuff like that. And there are times such designs can be helpful if you need those ticks in multiple spots as signals. In this case, we don't. In this case, all we cared about really on that whole design was just something that counts slowly, 0, 1, 2, 3. So we said remove all that confusion. And then when you're doing it, we might as well have something that uses the values over here. So, and it's like a 5-line module, so it really shouldn't take you long. Yeah.
Is there any way we could get you to like type up and email out your modified deliverables, just so we can see it in a
Yes.
more concise?
We can definitely do that.
Okay, or like update the lab or something?
I'll update the lab because then it'll be clear and I'll put a notice.
Okay, so that's before like this one is.
Yeah.
Okay, thank you.
All right, any other questions? All right. So take care of each one of those and we're good. At that point, we'll only have one more. So, and we've got a bunch more time. So if we need, ideally, I'd like us to keep as much pressure as we can on getting these done, because the sooner we're done, the sooner we finish. And the last one, I want to leave a lot to your own discretion on building, because it's kind of more of a game and counting and stuff like that. So it'll use a lot of the things you have. So I want to give you multiple weeks on that. But if we need time, you can let me know in class, and we can say when we have to do the demo for this. Fair?
Do you still want the LED output for input on the switches, like you had on line 9?
Which?
It's on line 9, yes, we did input, it showed,
Yeah, all those things.
do you still want the LED output to exist, or do you just want the
I think
switches?
that's-
Okay,
Every single one of them.
might as well leave it.
Yeah, I mean, it costs you nothing to leave it in, so you might as well just leave it in.
Okay.
Because you could just literally take that off and slam the rest of it. And I will scan these and send them to the group too. But you're welcome to take a picture.
Thank you.
There's a second sheet under there if people want to make sure they get everything. That was the clock counting.
Also, and we just have like well, I'm learning like.
I hope this is easier to understand than the other stuff.
It's much easier than the lab.
I didn't even notice it till literally.
I'm a big fan of easy.
And then regular foods.